All right, this is the second part of that worksheet. A 50-kilogram boy and a 40-kilogram girl sit on the opposite end of a seesaw. They sit on opposite ends. How far from the girl should the fulcrum be in order for the boy and the girl to be balanced? Here's the seesaw. Here's the boy. Here is the girl. They're both on the end. And the total distance is 3 meters. Okay, actually, I don't want to put it on the bottom. We know this whole thing is 3 meters. We are going to place this fulcrum, and we don't know where. So we don't know this distance x, and we don't know this distance y, but we know x plus y equals 3. All right. So where should we put it? Well, sum of the torques have to be equal to 0. This is going to be a torque. We'll call that torque 1. This is going to be a torque. We'll call that torque 2. We know torque 1 is positive, so we know torque 1 minus torque 2. 0 equals torque 1 minus torque 2. That is 50 kilograms. So 50 times, we'll say G equals 10. Did I put 10 in there? Yes. Hold on. Let me think what I did. Okay. Yeah, 10 works. It doesn't matter which one you use actually, but okay. We know that torque 1 is equal to 50 times 10, which is the force of gravity, times some distance x, minus 40 times y, times 10, times the distance y. And I have 2 variables, and I have 2 unknowns, but I have 2 equations. So we can plug in, I don't know, I can solve for x, which equals 3 minus y, and plug that in for x. So now I have 50 times 10, it's 500. And I'm going to multiply it times 3 minus y, minus 400 times y, and all that equals 0. And I will solve for y. And y is the distance the fulcrum is located from the girl. And y is equal to 1.66 meters. Okay, let's do number 3. This one is important. They're all important, but anyway, the velocity vectors are drawn to scale. Let's read this. 4 particles, each of mass m, in the xy plane with varying velocities are shown. The velocity vectors are drawn to scale. Rank the angular momentum about the origin. What does that mean? That the origin has been defined as the axis of rotation. So we need to rank the angular momentum. The equation for angular momentum is its rotational inertia, which is its mass, times its angular speed. I don't have angular speed. I was given its linear velocity vectors. So I have to use a bridge equation. Vt equals angular, the radius times its angular speed. So I can rearrange that for Vt over r, and I can say the angular momentum is equal to its moment of inertia times its tangential velocity over its radius. Each one of these have the same radius about that origin based on its location on that axis. Okay, not all of them have the same tangential velocity. But before we continue, let's look at I. What is the I value for each one of these particles? Well, I is the sum of all of the masses times the locations squared with respect to the axis of rotation. So it's only one particle, so one mass, times its locations of each one of them, they're all same, times the Vt over r. So I can cancel that out. Mass times r times the velocity, tangential velocity. Every single particle has the same mass, and every single particle has the same radius. All I really need to do is look at to see which one has the largest tangential velocity. Well, let's look at A. It has, I have to take that little velocity vector and break it into its two parts. This B has a tangential velocity vector to this circle, right? We're assuming it's traveling around this circle. And so I got to break it into that. Well, not quite that one. I have to break that into a tangential velocity. That looks better. C already has a tangential velocity. It's already tangent to that circle. And D has 0. So D is the smallest for sure. So D is last. Angular momentum of D is last. The next one, the next smallest one is A. So there we go. And then the largest one is C. And then the second largest one is B. Well, there's the ranking. All right, number 7. I have a spinning plate in a microwave with a moment of inertia, I, so it has an I value that they gave us, about its center of mass at a constant angular speed. So there's its speed, omega. When the microwave ends its cook cycle, the plate comes to rest in some time, delta t, due to a constant frictional force applied to a distance r away from the axis of rotation. All right, so we have a force that's being applied at some distance r that creates a torque. What is the magnitude of that frictional force? So here's my disk, here's my maybe my direction of my angular speed, and it has some radius. It has obviously a moment of inertia that's related to the disk, and somewhere I'm going to have a force that's going to slow it down. So we'll just assume it's force of friction, and it's at some r value. I don't know exactly where it is, but I just know that it's a distance r away from the axis of rotation. And the question is, what is the value, the magnitude of the frictional force? Okay, at first you're thinking, how in the world am I going to solve that? One thing I would do is I see my answers. I see in my answers some delta t, some I values. And the next thing I would do, that might give you some indication of what I might need to use. The next thing I would do is look at my equation sheet. I have 2 equations that are related to torque and have something to do with this time. So I know that the torque, the net torque, right, is equal to its moment of inertia times its angular acceleration. And I only know of one torque that's causing that to slow down, and that's force of friction. So the other equation I might have of interest is that if I apply a torque, or the net torque, for some period of time, I'm going to have a change in angular momentum, which is equal to the angular momentum final minus the angular momentum initial. Okay, the angular momentum final in this case was 0 because it came to rest. So it, and the other thing I know is that the friction, the torque that's being applied to it, is the force of friction times the distance away from the axis of rotation. We'll have to assume that it was at a 90-degree angle and that sine theta is equal to 1. I probably should have done a better job of explaining that. Okay, so now I'm thinking that I'm going to have to use this approach, this equation, since I have a delta t in my problem. And in this initial angular momentum is an angular speed, omega, which is also in my answer. And so I'm going to rewrite that and continue to kind of build out that equation with my things that I know. I know the torque that's being caused by that force of friction is force times the distance away from the axis of rotation. I have a change in time, and the only, it's equal to negative angular momentum initial, which is the disk moment of inertia times its initial angular speed, which they gave me as omega. And I want to know force, so I could rearrange this equation for force, and that'll equal what I have shown. And I know that that's the force, and they asked for the magnitude, so I don't care about the negative. And here is my answer. All right. I have a comet or a planet that orbits a sun, and we want which principles of physics most clearly and directly explain why the speed of the planet is the same at positions A and B. A and B, although it's hard to see, it's approximately the same distance away. That's my interpretation. There's only two principles, physics principles, that we could use with the planet in orbit. We're going to have conservation of energy and conservation of momentum. All right, number 9. Find my paper. We have a force that's applied to a wrench to turn a bolt of specific rotational inertia I, which rotates freely about its center as shown in the following diagram. Which of the following correctly ranks the resulting angular acceleration of the bolt? Okay, so we know that torque is equal to moment of inertia times angular acceleration. The force that we're applying times its distance away, r, and we'll call the length of the whole bolt r, is equal to the moment of inertia times angular acceleration. And we'll rearrange that for angular acceleration. And that will be equal to force r over I. And then we'll look at each one of these bolts, okay? And kind of come up with that relationship. Every single one, so we have a force value, this is 2F, this is F at an angle, F at halfway. And then we have these I values. Oh, that is 2I right here. There we go. This is 2I. So 2I, I, 2I, I. Okay. All right, so let's kind of evaluate each location. So again, we want to know which one has the highest angular acceleration, the one that has the largest torque, essentially. And we also have to take into consideration the moment of inertia. So the first one is force and R and I, because so that is what we derived here. The force is F they gave me, R is the whole distance, and I is, in this case, just I. The second one is we have force. We're still located at its end, but this time I have 2I. So essentially I have a fraction of 1/2. Okay, the second one, I have 2 times F times R over 2I. So my halves are going to cancel. So I'm back to FRI, which is the same as A. And D, I'm going to have F, but I only have half of an R. And I have I, so I'm essentially, I can rewrite that as 1/2 FRI, which is the same as B. I'll come back to E in just a sec. And then F, I'm going to have 2 times F times R over I. So now that one's the largest so far. I have a factor of 2, or I'm multiplying FR over I by 2. And then in the third one, or back to E for just a second. In this case, I'm going to have force times the distance R times some sine of theta over 2I, okay? And so I have 1/2 times sine of theta. Sine of theta, that angle is going to be somewhere between 0 and 90, and it's going to be a fraction, and so I'm going to be even smaller than 1/2. So which one is, what do they say, ranks the resulting acceleration? I'm assuming we're going from greatest to smallest. So the greatest is F, and it will be the greatest. And then the next one is, well, let's see, F had 2. Then we have 2 of them that have no fraction, and that would be C and A. So then we have C, which must equal A. And then the next one is the halves, correct? We have 1/2 and we have 1/2, and they're equal to one another. So they are greater than B, which equals D. And then the last one is D, which has, I'm sorry, E, which has the smallest. So F, which equals A, or is greater than A, which equals C, which is greater than B, which equals D, which is greater than. Oh, there it is. Okay. All right, 12. A ball and a block of equal mass are situated on the ramps with the same shape. The objects are released from rest. They are released from the same height. Release. So we're starting from rest from the same height. They roll. The ball rolls without slipping, and the block travels without friction. And after leaving the ramp, which object travels higher and why? So here's the block taken off, and here's the ball taken off. Well, first off, it's a change in height. So there's probably going to be energy associated with it. They both start at the same height. They both have the same mass. They both have the same amount of energy. So we'll assume that's 10 joules, just to show you. Okay. The block travels down the ramp. It has no friction, and at that moment in time as it leaves, it's going to have 10 joules of energy, and it's going to be split up between potential energy due to gravity and its kinetic energy. So it, I don't know, we'll call that, maybe it has 2 in, I'll say 3 joules of potential energy due to gravity and 7 kinetic energy. I don't know what it is. I'm just going to use some numbers just to kind of show you, help you see it. What determines where the block goes in the sky or how high is its velocity as it leaves. Okay, so we have a projectile and we have some maximum height. What's going to determine how high it goes is its velocity in the y direction. And what's going to determine how far it goes is its combination of its velocity in the x direction and the amount of time that it's in flight. Okay, so this is the max height. I'm just showing you that to kind of give you a little refresher from first period or first unit we had. So that kinetic energy is associated with that velocity, okay, that linear velocity that it has at that angle as it takes off. All right, and we're just assuming that 10 was split up between 7 and 3. Now the ball has it rolled without slipping. That means that it does have static friction, because static friction is what causes the ball to roll. However, all of the work done by static friction is regained in kinetic energy, that's a rotational kinetic energy. That's what causes the ball to roll, and so we gain that energy back. And so it has at its final location potential energy due to gravity plus kinetic energy, but it has 2 kinds of kinetic energy. It has translational and rotational. So its potential energy due to gravity, it's the exact same ramp, and so it has to equal the same potential energy due to gravity that the block had at that location, which means that the 7 joules that is left has to be split between kinetic energy rotational and kinetic energy translational. And I don't know what the split is. We'll call it 4 and 3. Maybe its rotational is 3 and 4 joules for translational. And so the amount of energy that I will have in linear kinetic energy that is related to the velocity of that ball that determines my height is smaller. Therefore, its velocity in the y direction will be smaller because its resultant, its velocity at that angle is smaller, and its maximum height will be less. All right, so I use that to kind of hopefully review a whole bunch of concepts. So we know the ball travels higher because it gains, no, we know the block travel higher because it experiences no rotation, because when rotation is experienced, I lose some of my energy to that rotation, and therefore I don't go to as high of a height. Okay, one more to go. I have a 20 kilogram ladder of length 8 meters sits against a frictionless wall at an angle of 60 degrees. The ladder is just barely, just barely keeps from slipping. In other words, it sounds like it's at slipping. So we want to draw on the diagram. They probably should have done a better job of saying that there was no friction here. I know this. Let's see, a 20 kilogram sits on a, oh, they did tell me that. A frictionless wall at an angle of 60 degrees. The ladder just barely keeps from slipping. So I'm right at slipping, in my opinion. Draw the forces. All right, I got force of gravity acting on the ladder, which is equal to, they told me, 20 kilograms. And, oh, I use 9.8. I hate it when I do that. So we know the force of gravity. And then I have force normal from the wall, so I gotta make sure I write that. So, and I have force normal from the ground. And if I have static friction, the ladder is trying to go that way, it's trying to slip that way, so static friction is gonna go the other way. Okay, all right. Determine the frictional force of the floor on the ladder. Okay. Well, I have to sum the forces in the x direction, sum the forces in the y direction, and sum the torques, and all of those will equal 0. So, got to pick an axis of rotation, and I'm going to pick the location at the ground. It eliminates 2 forces. And so I'm going to start by summing the forces in the x direction, and I know they have to add up to 0. I'm going to assume right is positive. So I have force of static friction minus force normal of the wall, which basically states that the force of static friction equals the force normal from the wall. So if I can find the force normal of the wall, I have answered B. If I sum the forces in the y direction, I will add up to 0, and I have force normal of the ground pointing up, and I have to subtract force of gravity of the ladder. So I know that force normal from the ground is equal to force of gravity on the ladder, which is equal to the mass of the ladder times acceleration due to gravity, and I'll use 9.8, and that will equal 196 newtons. And then I'm going to sum the torques. And I have to, in my opinion, if I choose, I want that location for axis of rotation, I feel that you should come along and confirm which direction. So we'll call the force of gravity, we'll call that torque 1, and it's negative. And this force from the wall is torque 2, and it's positive. All right. So we'll sum all the torques. They have to equal 0, and that will equal torque 2 minus torque 1. So torque 2, based on this axis of rotation is that force normal of the wall times the total length, which they gave me as 8 meters, minus the force of gravity, which we know is 196 newtons, minus its distance away from the axis of rotation, which is 4. And, oh, we forgot some angles, did we not? Let's go back. We got to evaluate some geometry. This is 60 degrees. This is 30 degrees. This is 60 degrees, okay? So we got to determine the angle. Let's remember our equation. Force times r times sine of theta. And theta is the angle between the force vector and the r vector. So let's look at this force normal from the wall. Force normal from the wall. And here is my r vector. And so I want to know this angle. Okay, and that would be 60. So this will be sine of 60 degrees. And then subtract the torque 1, which is force of gravity, which is 196, times its distance away from axis of rotation, which is 4. And now let's see if we can figure out that angle. So here's my axis of rotation. Here's my distance r. Here's my force vector. And I need to know this angle. And that would be 30. Okay. Then I can solve for force normal of the wall because it's the only unknown in this equation. And if I know that, I know what I'm looking for B. Force normal of the wall, if you rearrange all of that, you will get approximately 56.58 newtons. So B is 56.58 newtons. C, determine the coefficient of friction between the ladder and the floor. All right, so definition of force of static friction is equal to the coefficient of static friction times force normal. And in this case, what? Force normal. So we're just looking at this particular section of this problem. It's the force normal of the ground. So we know it's equal to force of static friction times force normal of the ground. We know the value of force of static friction is 56.58 newtons. And we know the force normal of the ground, which we found up here to be 196. So I can solve for mu. And so the coefficient of static friction is 56.58 divided by 196, which is equal to 0.29. There you go.